doesn't seem to work. All right, so, whoop, what happened there? All good. All right, so today do hydrothermal alteration. I'll go through this at various paces so we can at least have a bit of a discussion. I brought some samples because I know Taylor's very keen to look at things that we can have a look at and discuss and go through it. So we talked about hydrothermal fluids yesterday and what their composition is and what they can do to surrounding rocks, and that's what hydrothermal alteration is. The main reason this is important is it's primarily used as a vector towards mineralization, specifically hydrothermal mineralization. So if you see certain hydrothermal assemblages, you know you're in an area where lots of fluids have moved through and potentially you might have metal deposition. So we've covered some of this stuff, but what happens is the fluids will interact with the country rock, and depending on the temperature of the fluid, depending on the composition of the fluid, and depending on the nature of the country rock, you'll get different interactions, and then you'll produce a new mineral assemblage that reflects those equilibrium conditions. So you're going from a scenario where the host rock is out of equilibrium with the fluid, or this boundary, and it's changing to a situation where it's happy and it's stable. So it's broadly a metamorphic process, but most of the time in metamorphism we assume that we're closed system, excluding water, whereas here we can move elements. You can gain or lose different elements in the rock. So that's called metasomatism, but that detail doesn't matter. So it's a little bit more complicated, and it's important to realise that hydrothermal alteration is fairly common, but most of the time, the changes you see around are probably related to other processes like metamorphism or something like that. But there is key signatures that you go, oh, this is a case where it's hydrothermally altered versus a different scenario. So that'll become important when we talk about different assemblages we look at later. Oh, and the other thing that can vary is pressure, of course. So here's an example of a fresh, looks like a diorite or gabbro, and an altered example. So you can get quite drastic changes. Sometimes it's fairly obvious, other times it's subtle. And so we will work through and we can talk about examples of ways that you can pick this apart. And like I said, sometimes you might just have the effect of hydration, so you might just hydrate the minerals, turn them into fluid-bearing crystals. Other times you might lose or gain different elements, and that creates different kinds of alteration assemblages depending on what is happening. And you get changes in the texture, the density, physical properties, all driven by what minerals are there. So the common case is a hydrolysis reaction, or essentially a hydration reaction. So in this case we have our happy microcline, potassium, aluminium, silica, oxygen. If we add, sorry, this is the wrong case, but yeah, it's on the next, I'll put it on the next one, make more sense. Here, but if we add hydrogen, we can change it to a muscovite. So very similar composition, but we're adding extra hydroxyl components at the end as a hydrous phase. We might liberate some potassium and we might produce quartz. So the incorporation of water has changed what is stable at those conditions. We go from something that's anhydrous to a hydrous mineral and we're potentially liberating potassium. And so these things can go further. You might go to a case where we have an andesine plagioclase, so an intermediate plagioclase. It's got combinations of sodium and calcium. You could incorporate hydrogen plus potassium, so you produce sericite, which is just a fine white mica or fine muscovite. And then we release other things like sodium, calcium, and things like that. So depending on the nature of this reaction, depending on its pH, things like that, we can produce a variety of assemblages, and we can liberate different elements that can either move away or potentially enrich other parts of the system. And this is just another example if we change mica to kaolinite, which is a clay. So varying degrees of how much hydration is going on, but inherent in this is you have, kaolinite is mainly something that forms fairly close to the surface, whereas muscovite form at deeper conditions generally. So you also have those broader controls on pressure and temperature. So that's a broadly hydrolysis reaction or a hydration reaction. This is an example of a base cation exchange. So here we're going from, again, our happy K-feldspar. We're adding sodium. We're going to change it to albite, so the sodium substitutes for where the potassium is, and we liberate potassium. So slightly different reaction that results in a different alteration assemblage and the liberation of different elements. This is going into more details about these sort of reactions, and the extent of how much potential removal of alkalis and calcium you have. You move from something to different clay minerals, in this case, montramillite, kaolinite, and quartz, or the extent of alteration. So you go from something with plagioclases to something with sericite and quartz, to something with kaolinite, alunite, and quartz. So you have variations on a theme based on how much fluid is moving through the system, how much alteration occurs, and at what conditions it's happening, and what nature of the alteration process is going on. So clearly the most important thing, one of the most important things then, is the host rock. So the same as in metamorphism, if you start with a chocolate cake, you expect to get something closer to a chocolate cake at the end. So in metamorphism, we don't lose those elements, but in alteration that will change, but what you start with is going to influence what you end up with. So we're broadly comfortable with what ultramafic rocks are, I assume, by this stage. Our primary mineralogy is dominated by things rich in iron, magnesium, and calcium. But if we hydrate these or alter these rocks, we end up with minerals that predominantly have magnesium, iron, and calcium. But they form into hydrous assemblages. Serpentine is a classic one for olivine. Talc might take over pyroxenes or things like that, and magnetite. But the key thing here is we're moving from dense assemblages, and hydrous minerals are usually denser, to less dense minerals. They've got a lower density because they're incorporating much more water. So if we alter an ultramafic rock, we should produce something that resembles what it was. So this is just some details on the reactions. There's a variety of different types, but here's an olivine to serpentinite, potentially brucite. So magnesium plus water, you end up with a hydrous magnesium silicate. And vice versa, andesite to serpentine, but you might end up with a tower and going forward. And then magnetite if you have an iron-rich portion of the olivine, most serpentinite is magnesium-rich. So in reality, olivine is a mixture of iron and magnesium. You can actually liberate the iron into magnetite instead of going into the serpentinite. So we can get into various stages of the chemical formulae, but this is a broadly follows the type of alteration called propylitic. This is mostly around variability in magnesium and commonly produces rocks that are greenish in colour. You have to take care because green schist facies metamorphism is probably one of the most common metamorphic rock around. A lot of the sedimentary rocks around here have experienced that. So they're dominated by chlorite, actonite, and plagioclase. So they have similar assemblages to what you would expect from propylitic alteration, and they're quite similar sort of processes. So take care. But the main thing is we see a change in the hardness of the rock. It becomes softer, more friable. Fabric will change. The rock becomes less dense. It might change its magnetism, depending if magnetite's formed or was in the original rock. And these are the sort of assemblages you would usually expect. So actonolite, which is a amphibole, calcic amphibole, chloride, carbonate, epidote, albite. So green mineral, green mineral, green mineral. You can see what ends up being green. So this is a broader guide to how you might recognise this form of alteration. I won't go through all of it, but it's most of the things that you do when you identify most rocks. So you'll be fairly comfortable, but you might find some unusual things like veining, foliation, brecciation, maybe some unusual minerals. So in an ultramafic rock, you might find quartz, which shouldn't be there usually, and things like that. So there's no point getting into too much detail there, but here's an example. If you compare the fresh dolerite, plagioclase, interlocking, and pyroxene, here's an altered version. It's got a pale greeny colour. I don't know if you guys can see that well. And it's got a bit more patchy form to it. It's not as homogeneous. And we produce things like epidote, albite, and chlorite and actonolite. Can you guys see that? Yeah. Yeah. But it's not too dark. So if we go to a felsic and intermediate rock, we're starting with a different cake mix. So we potentially experience different things. You have things like quartz. It's essentially non-reactive. Quartz is pretty stable and happy everywhere, largely because it's just silica and oxygen. Orthoclase and K-feldspar, similar to the reaction we saw before. You might change to muscovite, could go to a kaolinite or a clay. You might introduce carbonates. The pyroxenes, they're usually similar minerals to what we were discussing before, chloride, actonolite. Same with hornblends and things like that. So you see that the host rock, it controls what's really possible without introducing a whole bunch of stuff. So feldspars are commonly the thing that breaks down first, and they're quite unstable, and they're especially the calcic varieties. And so they commonly will change to albite, so they will substitute that calcium for sodium, which is stable at lower conditions, or you might form sericide or kaolinite. So here's an example of a pink selvage adjacent to the albite. So usually if it's pink, we assume that it's potentially potassium introduced, oxidized potassium. But we've also got plagioclase here. It's been pseudomorphed by sericide. And over here, albite is replacing this white little area there. Albite replacing replacing the original plagioclase. And we've got a big vein there that helps us tell. And so this is variations on a theme. We can see different coloured oxidised feldspars. You know, we're getting yellowy, greasy looking colours on the feldspars, so you can tell that something's changed. It's not fresh and glassy. It's starting to become opaque and of varying colour concentrations. And we keep going. In this case, we might have sericide. You could go highly potassic, introduce K feldspar. Examples, or a jewelera. Or you might silicify the rock. So that's when you're just introducing silica. And you know, we just produce a lot of potentially intense fine-grained silica masses, and we might retain part of the texture of the rock, or we might not. But we're certainly going to make it harder in this case. And this example, it's fully brecciated. So it was an andesite, but it doesn't look much like that anymore. So sometimes we have to take care to be sure we're come to what we see. The other alternative is carbonate alteration. So we introduce calcium carbonate, or at least CO2, and we produce different assemblages. Based on that, you know, you might form calc-silicates, and you're liberating different elements to stable the carbonate phases. So, yeah, this is where acid becomes handy. And this is clay, so this is a lower grade example, but we can discuss that when we look over here. So the feldspars commonly will, if you, at low enough conditions and low temperatures and with enough hydration, they will turn to a kaolinite instead of a fine-grained muscovite. So, for intermediate rocks, andesites, they're reasonably mafic. You might find propylitic alteration. So again, you'll see things like actonite chloride, albite epidote, so you get that greenish colour where you're related to magnesium. You might get carbonates, but it'll be slightly different, the ultramafic rocks, because you probably have quartz hanging around. So for more let's go to, oh yeah, that's fine. For more felsic rocks, the changes are a bit different. They're commonly pink or white, so and so they could be related to introduction of potassium, so we call it potassic alteration. If they're dominated by sericite or clays, they call what we call argillic alteration. But we can also get things like carbonate coming in. So the main thing to sort of see is that there'd be a variability in colour. It always helps if you know what the host rock is. What should it look like? What does it currently look like? If you don't have the host rock, what are the mineralogy? Is it soft? Is it hard? Those same broad aspects that we're discussing before. Yeah. So this is some details specific to intermediate felsic rocks, but it's just variations of the thing compared to ultramafic. So we start to work through these in different priorities, and there'll be key aspects that will help between different rock types. Here's an example, and there's another example up front. A fresh monzonite versus an altered version. Clear difference in coloration. What kind of alteration type do you think that one is?
We just discussed the
Propylitic, yeah. So it's gone a greenish colour. We're producing hornblende, going to some sort of chloride. So that's a propylitic style of alteration. Sedimentary rocks, slightly more complicated because we have diverse proteins. So you the original rock is much more diverse. So the same as in metamorphism, you know, you can get anything from a marble to, you know, a luminous schist to, you know, volcanogenic material that might be reminiscent of a basalt. So this inherent compositional control will influence what's left. What it alters to, and you can have much more diverse sort of mineral assemblages. So again, you have these broad types. So we've broadly covered these ones. You know, muscovite goes to sericite and clay, but we're more likely to have carbonate minerals, which are highly reactive. So carbonate assemblages are likely to be more common, and we're usually in a luminous system because we have lots of clays, and so that will influence the sort of alteration. So we get a dominance towards sericite and clay alteration assemblages, but that doesn't preclude that we can't get chloride if we add a lot of magnesium or react it out. So here's a mudstone. We broadly know what a mudstone should have in it. You know, mud-sized particles, predominantly of clays. And you know, some people call them agilites, but that's reasonably outdated these days. So if we're going to replace clays, we commonly replace them by things like sericite, because it's rich in aluminium, potentially potassium. So sericite is just fine muscovite. If we can introduce magnesium, we might be able to find chloride. So it's the two main variabilities. Here's an example of an altered mudstone. This is a propylitic alteration. We've got chloride. There's mainly the black areas. We have a bit of clay, we have pyrite, and we have some sericite. So the pyrite's a nice big coarse crystals in this case. So the changes are much more subtle relative to an igneous rock, largely because we're starting with a fine grain size. And here's a similar example, but it's got an obvious big vein running through it with sulfides in it, which helps sort of tell us what's going on. But the sort of alteration has sort of gone towards chloride with a bit of sericite, so it's fairly weak and of low grade. Sandstones. You know, if you have a quartz-rich sandstone, not much is going to change. They're a pretty boring rock to begin with, and they just get more boring. But you might get veining and things like this, or you might get hematite. So you might make it a bit more interesting, but they're fairly unreactive. Here's a greywacke. So a greywacke is more immature, so it's got a diverse mineralogy that enables more reactive minerals to be stable, feldspar, ferromagnesium minerals, potentially clays. In this case, we have a pale pink vein of epidote with garnet. So it's a calcosilicate sort of assemblage, and yeah. So this is a reasonably high grade if we're getting garnet and epidote alteration assemblages. So that's not overly common. Conglomerates, because they're so heterogeneous, they can make this spectacular photographs, but the fine grain material is more reactive compared to the coarse grain material. Why might you think the fine grain material is more reactive than the coarse class?
Surface area.
Yeah, simple as surface area. So it's more access to break down material, and commonly the class, you know, most conglomerate class, a lot of the time they're quartz rich or something like that, whereas the matrix is full of muds or more reactive material. And in this case, the green colour is coming from copper minerals oxidized copper minerals. Calcareous rocks, very reactive. That's why skarn deposits are very profitable, and that's largely related to the fact that they're alkaline. So the hydrothermal fluids moving through them are commonly acidic. So you have an acidic and an alkaline mixing. It's a nice place to have a reaction, and the metals drop out. But that also means we can move around a lot of base cations. So in calcareous rocks, you commonly can replace, you can introduce iron, you can introduce magnesium, and you can introduce when you have calcium, so you can liberate it. So you might get things like garnet, if you can add some aluminium, epidote, calcium aluminosilicate, diopside, so calcium iron magnesium pyroxene, or even sometimes you can get phalonitic olivine, so iron-rich olivine in some skarn deposits. Here's an example. We've got some garnet. It's very pale pink. It's a bit hard to see here. We've got moly, so there's our ore mineral, and this paley green here is a pyroxene, known as diopside. So it can have a quite spectacular effect on the alteration of these rocks, or in this case potentially even the ore minerals. So again here, variations on a theme, changes in the form of the rock, changes in its fabric, its hardness, potentially its magnetism, and we might see obvious things like veining or the introduction of carbonate material. For sedimentary rocks, it's a bit more challenging, but try to use the features of the host rock to your advantage. Does it still maintain some degree of layering? You know, is that bedding? How is the grain size vary? What kind of assemblages have we formed? Are they highly aluminous, or are they weird carbonate sort of minerals? So these are the sort of telltale signs for establishing the protolith. Look for textures. What does the texture mimic? What a granite might look like? Is it porphyritic? Is it bedded? Metamorphic rocks can be challenging, but you might see very coarse metamorphic crystals that are foliated and overprinted. Try and find if there's any original mineral still there. Is there quartz? Has it been introduced, or is it an original thing? That might tell you it's not ultramafic and maybe it's felsic. Hardness, they generally get softer. Look for sedimentary features. Grain size for sedimentary rocks, and for calcareous rocks you usually see a major change, and so it can be quite obvious, but that also means it overprints a lot of the relic features. So that's all I sort of wanted to go through, but there's a few examples here we can discuss. So we have, well, some of these are fairly obvious. If there's the fresh rock, here's an altered rock. But the main thing to work through is, there's a variation on the theme, so try and match, work through and figure out, firstly, which one matches which fresh rock. These are the altered ones. And also what style of alteration is going on. See, just to begin with, start to feel the differences. I mean, that one's a lot lighter. This one's an obvious colour change. I'll just stop this. So what's the fresh rock to begin with? Is it igneous, metamorphic, or sedimentary?
So at least this one's igneous.
Yep. They're both igneous.